This lecture we are going to continue with the liquid extraction. So what we are going to cover in this lecture is I will try to show how to draw some flow sheet, and then we will use this flow sheet to perform some mass balance calculations. And I just want to mention this is going to be a bit of a pure chemical engineering topic, because mass balance is probably the chemical engineers, they know how to perform. But even if you don't know how to do it, I can explain it. No, it's not a tough concept. It's really easy. All you need to know is whatever the mass that goes into some unit, the same mass will come out. Yeah. So something like mass in equal to mass out, or if you, I think everybody know law of conservation of mass. Yeah. So nobody can create a mass or nobody can destroy the mass, which means mass is going to be conserved, and that rule also apply in any chemical engineering unit operation. So if you have something like an extraction unit, if something goes in, if 1 kg goes in, we will get 1 kg out in total. So mass will be conserved. So you won't get 1.5 kg or 0.5 kg. Yeah. So whatever goes in, that comes out. So that's what we are going to do. But we are going to give some notations and some fancy equations to make this to make something useful out of this concept, mass balance concept. And then we are going to do some, we are going to see some graphical procedures, or if you want, we can call them as rules, certain set of rules that will make your life a bit easier if you want to design an extraction unit. Yeah. So this the graphical procedures that we are going to cover, it might look a bit weird, but once you understood how like each and every rules, just assume like these are some rules that's going to make your life easy. So just if you take it that way, then it will be easier to study. So these graphical rules, so what are they? So this is to exploit your ternary diagram to perform design calculations. I already said to you how we perform some experiment if you want to get a liquid equilibrium data, and then I already showed you how to plot them on a ternary diagram. So we went very slow for a reason. Yeah. So I'm 100% sure now you all might have practiced how to plot your liquid equilibrium data on a ternary diagram. So if you know that one, then we can go to the next step, which we are going to learn in this lecture. Yeah. And then we are going to solve a problem. Okay, coming back to the same thing, like this ternary diagram, I forgot to mention. So this ternary diagram, at the moment, all you know is like it's some triangle, and you have some liquid equilibrium line, and you know which of the components are miscible, which of the components are partially miscible, and then you know how to what's the liquid equilibrium line is, and where you can get your phase separation, where you will see your homogeneous mixture. So you all know these details, but what we are going to do is like we are going to make some simple rules, and then you are going to remember those rules, and then we are going to design some liquid extraction unit. So I will even recommend you to take a pen and paper, just try to whatever I'm going to do, especially when I'm going to talk about some rules and some calculations, try to repeat it immediately. Yeah. So pause the video, try to take a note, repeat it, so that way it will be easy to design a liquid extraction unit. And one more thing I want to say it again and again, like it's better you, whenever I upload a video, try to watch it immediately. Like if I am going to upload some video today, try to watch the video completely, and then try to repeat the problem, like are the derivations, or in this case we are going to throw some set of rules. So try to write it on a paper and try to think how the rules work like and how to implement. Yeah. So and then we are going to solve a very big problem. So you might have learned, many lecturers would have said to you, like there are few things that we can learn or we can easily understand only through solving some problems, and liquid extraction, that's a very good example for that. So I will show you how to Anyway, I'm going to explain the rules, and then I will show you how to implement the rules, and then we are going to perform some mass balance. We are going to derive some equations based on the law of conservation of mass, and then so it might look a bit weird, but once you solve the problem, then everything will come together. So you will understand why did we perform a mass balance calculation and what these rules are about that allows you to get the maximum information from your ternary plot. Yeah. So your ternary plot looks like a very simple diagram, but in this lecture you will understand. It will help you to get many more information, especially when you are going to design a liquid extraction unit. Yeah, and just to try to remember, we have a liquid extraction. There should be some phase separation. One side should be extract, one side should be raffinate, and both of them might contains three of these components, C, A and B, C, A and B. So you all know what is C. C is your solute, A is your carrier liquid, B is your solvent, and you all remember, I hope you should remember how a liquid equilibrium line looks like in a ternary plot. So this one, so we will have clear separation in this region. In this region everything will be homogeneous, and then this is something very important you must remember for this lecture. So this is your ternary diagram, and then you have your liquid equilibrium line, and then we know which side is your raffinate arm. This is your raffinate side, and this is your extract side. And you know we are plotting C on the top, A on the left hand side, B on the right hand side of your triangle. And this is something very important, tie lines. Tie lines connect the composition of your feed and your composition of your extract and your raffinate. So this point, this is your extract side, this point is your raffinate side, this point is your extract side, and whatever the composition we have here, A comma B comma C. So these are the things you should remember for this lecture. Then it will be easy to do few things. And then I'm going to jump directly into the topic of mass balance. So mass balance, so this is a very simple rule. Whatever that goes in, that comes out. So I know chemical engineering students, they already studied this in the first year or second year, I think. So for the pharmaceutical chemistry students, just to follow this, whatever I'm going to say. So just imagine this is some unit. If you have 2 kg in one stream, and if you have 1 kg in another stream, and just imagine you have 2 output streams. If you get 1.5 kg in one of the stream, this remaining should be, it's very easy to calculate. So 2 plus 1 is 3 kg. You have 1.5 kg, so this will be 3 minus 1.5 kg, so 1.5 kg. So what it means is like in the output stream we have 1.5 kg plus 1.5 kg, so 3 kgs out, and here 3 kgs in. So what it means is like your mass is comes out. So this rule is okay. And then next, if you take to the, it's the same unit, same rule, 1 kg goes in one stream, 2 kg goes in another stream, and imagine 1.5 kg comes in the first output stream, and the remaining 1.5 kg comes in the second output stream. And for the moments, let's assume the stream 1, it contains, let's put C, it contains 50% of C, and then the stream 2 contains 50% of C. So what's the mass of C that goes in this stream? It's exactly 1 kg multiplied by 0.5. So 0.5 kg goes into this stream, first stream, and here it's the same. You have 2 kg. Out of that, 50% will be your compound C. So what's the kg of C that goes into this stream? Is just 2 kg multiplied by 0.5. So that should be 1 kg. So which means 1 kg of C goes into the stream 2, and 0.5 kg of C goes into the stream input stream 1. And if you look at the output here, I just assumed here, like in one of the output we have 35% C coming out. So 35% C in output stream 1, and in output stream 2, if I ask you to calculate the percentage C that comes in the output stream 2, how to calculate that? Again the same rule, mass in equal to mass out. So in this case 1.5 kg, and 35% of 1.5 kg is your percentage of, sorry, is C. So which means mass of C in this stream should be equal to 1.5 multiplied by 0.35. That should be equal to 0.525, I think. It should be equal to 0.525 kg. So let me calculate it. Yeah, that's 0.525 kg. So I said to you in the stream 2 we have 1.5 kg. So what will be the remaining percentage here? So the remaining percentage will be 1.5 kg so mass in that goes inside is mass of C that goes inside is 1 plus 0.5, that's 1.5 kg. So here it should be the same. So here if it's 0.25 kg, the amount of C in this stream must be 1.5 minus 0.525. So that will be equal to 0.975. Sorry for going bit slow. 0.975 kg. So this will be exactly like around 65%. 65% of A. So in this case we calculated everything just using a simple calculator. Yeah, so for this you don't even need to know some chemical engineering concept. These are like just using the common sense, like 10% of 100. That's what is this, just 10. Yeah, so these are the rules that we are applying. Yeah, so in this case 0.975 kg. So we know that 1.5 kg is 100%. So 0.975 kg will be 0.975 multiplied by 100 divided by 1.5. That will be equal to 65%. So 65% of the C's should come in the stream 2. So these are like pure mathematics. We didn't give any notations, anything. Yeah. So but for the moment, let's change the color. But imagine if this unit is an extraction unit, then we can give some notations. Let's call the stream 1, let's call it as a solvent, yes. And then stream 1, we can call it as a feed solution. And then the stream 2 that comes in the top, we can give some notation, say extract. And this stream 2, we can give some notation R. And then this percentage of C, or we can express them in terms of mass fraction instead of percentage. We can just divide it by 100, it will give in mass fraction. So we can give some notation XF that refers to the fraction of solute in feed, something like that. Just assume this C, whatever I said, that's your solute in stream 1. And here this 50% C, we can give some notation, why not? So say something like what notation we can give, say like XS for example. Just want to stick to some common notation. No, let's give YS. we can give ys, and then for this value, this 0.525 or 35% C, we can give some notation instead of this number. Let's call it as say like x1, and then here whatever we calculated 65%, or we can give some notation, say like y1. I just want to correct few things. Okay, it's better we name this output stream 1 as raffinate. So let's, instead of E, let's assign the word R, and then the second stream, let's assign, let me call this one as extract stream. So let's give the notation E instead of R. Yeah, and then the mole fraction of solute in raffinate, normally we use the notation x1, so this part is correct. And then this the solute fraction in the extract side, normally we use the notation, the common notation is what we use is y, let's call it as y1. So this is the correct notation. Yeah, so always try to remember that. So if you like, for use this not simple things to remember, rx and then ey. So don't forget. So in the top you have raffinate, in the bottom you have extract, in the top you have raffinate, and then the solute fraction in raffinate side will be x1, and then the solute fraction in the extract side will be y1. So we are going to assume that there is some unit which is where we are going to perform some liquid extraction, and then we are going to give some notations and try to derive some set of equations that will make your life a bit easier. Yeah, so let's do that mass balance calculations. So I already showed you something. So this is our extraction unit. So let's assume we are having some feed solution. That feed solution should contain your carrier liquid plus your solute. Sometimes it might contain some trace amount of solvent, but for the moment let's put carrier liquid plus solute, and then your solvent. This is the solvent, pure solvent. Sometimes it might contain other compounds, so for the moment let's assume this is your pure solvent, and then we get our raffinate side, and then we also get our extract side. Yeah. So let's assume the mass of feed that goes inside, let's give some notation F, and then the mass of solvent that goes into the extraction unit, let's give some notation yes, and then the mass of raffinate that comes out. So this raffinate might contain your component A, B and C, but let's assume the total mass of your raffinate is some number, and that number let's denote it by some notation. Let's call it as R. And then you have your extract side. Extract will also contain three components: your solute, solvent and your carrier liquid. And then whatever the composition, we will call the total mass of the extract side by some notation, say E. I hope you all are following this one. And then for the moments, let assume at the moment let we think only about solute. Yeah, so let's assume your solute concentration in your feed contains some percentage of your solute, So let's, the fraction of solute in your feed, let's give some notation xf. So all this notation correspond to solute. Not, we are not thinking anything at the moment about carrier liquid or solvent. The fraction of your solute in feed, say it's x of. Maybe your feed contains say 80 percentage of solute, 60 percentage of solute, 40 percentage of solute. Whatever the mass fraction be, that mass fraction we call it as x of. Imagine if your feed contains a carrier liquid plus your solute. So if the total mass is say 100 kg, so 100 kg is your F, and say like out of this carrier in the feed 50 percentage is your solute, so which means the mass fraction is exactly 0.5. So 100 multiplied by 50 by 100, so that will be 50 kgs. So or if you express in terms of mass fraction, it's 0.5. You just divide 50 percentage by 100, that will give you in terms of fraction, mass fraction. So 0.5. So this one we are going to use some notation x of. So that's what I did. And then the same rule goes for solute. If your solute contains some amount of solvent that goes inside, if your solvent contains say some bit of solute, and say like a tiny fraction, maybe 1% of solute, and instead of giving some number, we will give some notation. So let it be ys, and then in the raffinate side, just assume your raffinate contains some percentage of your solute, or if you want we can use the word mass fraction of your solute. That will be equal to x1, and then this in the extract side, the mass fraction of your solute will be equal to y1. So we are just giving some notation. So imagine if for extract we get 50 kgs of extract, and in that 80 percentage is y1, or mass fraction of 80 percentage is your solute, or if you want to express in terms of mass fraction, 0.8. That's the mass fraction of your solute. Mass fraction of your solute. So this is nothing but y1. And then one thing, remember the notations that we are using now. For both solvent and extract, we are using the alphabet y. Y suffix s is something refers to the solute concentration in the solvent, and then y1 is the solute concentration in your extract side. And then in the top we use the same notation, x for feed and x for raffinate. So don't get confused. Just remember the notations. So don't mix things up. Don't put y in the raffinate side and x in the extract side. So always remember rx fx, and then sy ey. So this will make you to remember what is what. So don't forget, don't get confused with the notations. So the way I am writing on the notebook, you will understand only if you are following the videos. So you must listen to me what I am saying. So, and if you want, you can take your own notes by yourself. I don't know, when I studied, I used to take a note. Whatever my professor teach, I write it line by line. I don't know is that good idea or not, but I did. So this is what we did so far is like we take some extraction unit and then we put some notations. And then I think so far everything looks fine. And then we can even put some notation S1 here, S1. So what is this number 1 here, S1, E1, or not E1, maybe, okay, yeah, we can even give the notation E1. We can put suffix R suffix 1, S suffix 1, Y suffix 1. So what is this 1 means is like at the moment we are doing in the one unit operation, yeah, but in industries they will connect 1, 2 and 3, yeah. They can perform the, they will move the extract and raffinate to the next stage, and then they will separate even more, and then they move it to the next stage, and then they will even separate more, yeah. So we call it as multi-stage extraction, but we are not going to cover this in the module. We are going to do only like a single stage extraction unit. So let's stick to this notation. See, it's not a bad idea to put this suffix S1, E1, Y1, R1, X1, yeah. For the feed we don't have to put any suffix because feed is going to be only one time, yeah. So feed is your starting material. I think so far everything is fine, I think. So I'm going to solve some equations using the concept of, not even concept, it is the law of conservation of mass. But before doing that, I'm going to try to not try to remember, I'm going to show you something that we need to consider on a ternary diagram. So you all know this is the ternary diagram. Ternary diagram. So this is your liquid-liquid equilibrium curve or line, and then we have a clear phase separation here. You all know these things, and just assume I put some, and this is your 100% solvent side, 100% carrier liquid side, 100% solute side. You have C, you have A and B, cab. Never forget that word. And then now I just put something. You need to know this line, at least this this particular fact, before we are going to solve some material balance, yeah. We are going to perform some material balance. So just imagine we have a feed solution that contains a carrier liquid plus solute, and just assume this feed solution contains 0% of your solvent. So which means this is a normal statement. You have feed solution that contains solute and carrier liquid, and we are going to we use normally liquid extraction to remove solute, yeah, using some solvent. So we are using a pure solvent to extract the solute from the feed. So pure solvent, what does that mean? It means that solvent contains 100% of solvent. So 0% of carrier liquid and then 0% of solute. I'm stating the obvious, but it makes some sense. So what we need to know. So if I ask you to draw a feed line on this ternary diagram, so how to do that, yeah? So I will show you how to that is the reason that we are covering this one at the moment before doing the mass balance calculations. So how to draw that feed line. So let's assume our feed solution. So I said to you we have a feed solution that contains 0% solvent, but I didn't tell what's the percentage of solute, yeah? So let's assume that feed solution contains 60% solute and 0% of solvent. So what will be that? So it will, the remaining 40% will be obviously your carrier liquid. So if I ask you to plot the F, your feed point, let's call it as feed point, and then it's even use some notation, say F, feed point. So if I ask you to plot on the ternary diagram, so what we have is like this F contains, in a normal day it should contain C, A and B. So C is what? 60%, which means 0.6, or even you can put 60%, and then your F contains A is your carrier liquid 40%, and B is 0% of your solvent. So where it will lie on the ternary diagram. So let's choose these 2 points, 60% of C and then 0% of solvent, which is B. So we know that if you go to the ternary diagram, let me use a different color. So this is your 100% solvent, and this baseline, that's your 0% solvent. So if you come back to this problem, this is 0% solvent should be somewhere on this baseline of your ternary diagram, and then 60% of your solute, which is C. So this point is your 100% C. Just follow the green arrow which I am drawing now. So 60% solute will be somewhere around here on this line. So this will be 60% of your C. So I hope you all are following this one. So if I ask you to locate the feed point, so it will be exactly here. Your F point will be here. So this point corresponds to 60% solute, 0% solvent, and obviously the remaining will be 40% of carrier liquid. So if you draw this line here, that will be automatically equal to 40% carrier liquid. So what we saw now is like how to locate the feed point, which is F here, yeah, and then we go back to the same simple problem. This is a very easy statement, yeah. And then I said we are starting some liquid extraction experiment with 100% solvent. So what is this like? What I am doing now is like we are performing some liquid equilibrium extraction experiment, or we need to perform something like that. So you have your starting solution that contains 60% solute, and we need to remove that using 100% pure solvent. So if I ask you to locate the 100% pure solvent point, it's very easy to find. Let's go back to this diagram. Again, maybe we put a pink. I don't know, green is not clear, I think. So this point is nothing but 100% solvent. So if I ask you to draw something called as a feed line, all you need to do is like we first locate the feed point on the ternary diagram, and then locate your 100%, locate your solvent point. Sometimes your solvent might contain impurities. That time it won't be exactly at the end of this triangle, the corner of the triangle. For the moment we are using 100% solvent, so we locate this point, and then we have to connect these 2 points. So that's your feed line. So that's your feed line. So I hope you all can follow this one. So why are we drawing this line? We have some reason to do that. And just assume there will be some at any point here, any point here, any point here, any point here, we will have some mixture. Yeah, so try to remember this word, any point inside this, under the liquid equilibrium line, we will have some mixture. Yeah. So we have a feed line at any point here, we will have some mixture. Yeah. So I think this is enough for the moment. I think it's good to go to see what mass balance is about. I think I will stop recording because last time whenever I this is the second time I'm recording this video. Yesterday I recorded this one, and then suddenly after 1.5 hours my tab crashed, and then I couldn't recover the file. So I will save this one and then I will continue in the next video. Thanks for listening. I'll quickly show one more time what we did. So we have our ternary diagram, C, A and B, and then that's our liquid equilibrium line, and then we located the feed point, and then 100% solvent. So this is nothing but our this, if you want we can call it as S1. If you go back to the notations that we used here, where is that? If you come back here, so we have something called F, we have something called S1. So that's what we did. Where is our F and where is our S1? Based on the mole fraction of each component in the feed and in the solvent. Yeah? So if you want we can call this point as S1 to maintain consistency, and then we are just connecting these two lines. So if you want we can call it as something like a feed line. So I think this is enough for the moment. Then why we plotted this graph and this feed line is like, if we have any mixture at this point, and if we have any tie line that cuts through that point, say this will be your extract side, this will be your raffinate side. So let's stick to the same rule, E1 R1. If we come back to here, this diagram, we have E1, we have R1 here. Just follow we have R1 and E1 here. So they are connected to something with your tie lines, E1 and R1, E1, R1. And if you want to know, like, just imagine we have a tie line and we have the feed line, and if you want to know what will be the composition at this particular point where the feed line cuts your tie line, say any tie line, it can be this tie line or it can be another tie line, then if you want to know the composition at these points, then we need to have some equations, expressions. So that's what we are going to derive. So let's do that now. And why we are so interested in calculating this point, soon you will understand when we are going to solve that very big problem. Yeah? So let's do the mass balance. So I'm going to draw one more time all the notations. So let's call it as liquid extraction unit. Say this is like a stage 1 something. Your feed XF, solvent S1 comma YS, and then your raffinate R comma X1, your extract. So what we are covering now is pure engineering. Yeah? So this is what engineers do. Like we have some ternary diagram, and then we will try to make use of the ternary diagram. First we will do some mass balance calculations, and then we will exploit the ternary diagram furthermore, and then we will design a whole unit, and then we will try to even answer like say like let me see, I have a problem which I have. So if you start something from a feed solution that contains, say, like 50 percentage of your solute, and then if I ask you, like, what's the amount of solvent that I need if I have to remove 90 percentage of your solute from your carrier liquid, then we need all these expressions that we are going to derive, and we also need that ternary diagram, and you also need to know how to draw the feed line, how to identify the point where it cuts in your tie lines and so on. Yeah, so but anyway, this is a bit tough topic, so I know that it's going to be tough, especially if you if you are studying, or if this is your first engineering module which you are learning at the moment. But just stick to the rules. Yeah, so there are, whatever that we are going to see, that's like a universal rule to design a liquid extraction unit. So it might sound tough, but you must practice. Yeah, so the only way to survive this type of design problem is to practice in home, and try to take notes, and don't have to remember everything, but but take a notes, like step 1, step 2, step 3, step 4, and then just apply the rule. If Because in the exam, if I'm going to ask some questions related to this type of problem, or if sorry, if I'm going to ask some problem related to liquid extraction, you will have only 3 hours of time, so you will have also other questions to answer. So you can solve the problem only if you already know how to do it. Yeah, so take the graph sheet, plot immediately, you identify those lines, and then apply the mass balance equation, calculate the values, and then give the answer. Yeah, so it's not going to be easy. So I recommend you to practice well in the home, so which means you can solve the problem very easily. If you don't practice, it's going to be very tough. And also, like, if you think like you can watch the video in the last minute during the exam time and then repeat the calculation, it's not going to be very easy. Yeah, I think the first part is already 30 minutes, and this one will go for another 1 hour. So in the exam time of 3 hours, you cannot play all of them, and then you cannot repeat the procedures. It's going to be very tough. Yeah, so better try to do it in the home. Whenever I upload something, try to practice, and then it will make your life a bit easy. So let's derive this one. It's not even a derivation. Yeah, it's something like we are going to state the obvious things, but in a mathematical way, using the notations which we assigned. So we know that mass in is equal to mass out. If this rule is true, then your feed plus solvent, that should be equal to extract plus raffinate. So your feed is F, your solvent is S, that should be equal to E plus R, and we are using some notations like S suffix 1, E suffix 1, R suffix 1, and this should be equal to mixture, the weight of your mixture. So which means feed plus solvent, that should be equal to 2 kg, extract plus raffinate, sorry, if feed plus solvent is equal to 2 kg, extract plus raffinate should be equal to 2 kg, which means your mixture of any of these two, feed plus solvent or extract plus solvent, that should be equal to 2 kgs as well. So that's what I wrote it. That should be equal to, let's call it as M1. Yeah, maybe we can even give some equation number 1. And now let's only focus on the solute part. Like, we have some percentage of solute in feed, some percentage of solute in the solvent, some percentage of solute in the raffinate side, and some percentage of solute in the extract side. So the total percentage of solute in, that should be equal to the total percentage of solute out. So how to do that? It's very simple. So we know what's the percentage of we know the mass fraction of solute in the let's write it in the word so then you will understand. Say mass fraction or maybe not mass fraction, mass of solute in feed plus mass of solute in what? In solvent. That should be equal to mass of solute. Your solute is not going to disappear, yeah, because mass cannot be destroyed and mass cannot be created either. So mass of solute in raffinate plus mass of solute in, I'm going a bit slow for the students who do not have an engineering background. Yeah, sometimes I even feel like it's not fair to give such hard topics to students who do not have engineering background, you know. But anyway, that's why we are making these things a bit more simpler. But on the other hand, you will have a very nice opportunity to learn something from the engineering side. In fact, this is such a beautiful module. You know, you study many things that chemical engineers study for 4 years. You study all the basics in one module, yeah, so that's not bad idea at all. So mass, so this is something we can call it as a mass balance for solute, or like chemical engineering we call it as just purely solute mass balance. So mass of solute in feed, mass of solute in feed is nothing but mass of feed multiplied by the mass fraction of your solute in the feed. So the same rule apply for the mass of solute in the solvent. So this is nothing but, this is equal to mass of feed multiplied by mass fraction of your solute, not your solute, mass fraction of solute in the solvent. So the same rule apply for mass of solute in raffinate and mass of solute in extract. Yeah, so I hope you can understand that. So what is this? So mass of solute in, mass of feed we know is something like F, and mass fraction of solute in the feed is XF. It's the same rule, like mass of feed, sorry, mass of solute in the solvent is mass of solvent multiplied by mass fraction of solute in the solvent. We know mass of solvent is S1 multiplied by mass fraction of solute in the solvent is YS. Never get confused with these notations, yeah. Please keep these notations in the mind, yeah. So there are so many books in chemical engineering, and for some reasons everybody is following different notations, and I hate that sometimes. So try to keep these notations for this module. Fix this notation in your mind. So X is something we refer to the solute in the feed, and we also use X to refer to the solute in the raffinate side, yeah. So remember this, Fx Rx and then Sy Ey. So I hope you all can follow this one. So if you want, I can even write it, yeah, why not? Let's go a bit more slow. Mass of solute in raffinate is equal to mass of your raffinate multiplied by mass fraction of solute in the raffinate So this will be nothing but mass of raffinate is R1 multiplied by mass fraction of solute in the raffinate side is X1. Yeah, so let's do the final one. Mass of solute in the extract side. I know I'm going very slow, but it's okay, because we're going to solve a big problem at the end of this tutorial or lecture. At that time you should know what we are talking about, yeah, so that's okay. I don't want to finish the module everything quick and you learn nothing, yeah, that's a horrible idea to do. So this will be like a mass of solute multiplied by mass of your extract multiplied by mass fraction of your solute. In the extract side. So this is nothing but, what is that? Mass of extract is E1 multiplied by, what is this? Mass fraction of your solute in the extract side. This is Y1. So always remember this notation: Rx, Fx, Ey, Sy. Yeah, I think this is fine. So now we can perform a solute balance. Solute balance, I think I wrote it before, yes. Solute balance is this one. So we are going to plug in those values, which we, not values, these expressions, Fx, F and so on. So that will be nothing but F xf plus S1 ys equal to E1 y1 plus R1 x1, and this will be equal to some mixture multiplied by fraction of your solute in that mixture. So if you want, we can even, so whatever this will be equal to some mixture multiplied by the solute fraction in that mixture. So this will be again equal to mixture multiplied by solute fraction in that mixture. So this is one equation. I hope you all can follow this one. This is not tough one, in fact, this is something like we know that if you don't use this notation, it's easy to state what is what, yeah, like it's not tough, but all you need is that a tiny bit of understanding and bit of imagination, yeah. So just imagine if you have a box, you have like I don't know, say like 2 red balls and then you have 2 blue balls. If I ask the percentage of red balls is 50 and then percentage of blue balls is 50, yeah. So that's the same rule, but we are applying in terms of the solute composition in a mixture, yeah, in a fluid mixture. I hope you all follow this one up to this stage. It's really important. You should understand what a mass balance is about and how to perform a mass balance. So these are simple rules, like we can, like one, if, how do you call, like you take the simple ball experiment. You have a box, so if you have say like two red balls that goes in, and then you have 2 green balls that two red balls that goes in, and 2 blue balls that goes in. So the total will be like 2 red plus 2 blue, that will be equal to 4, and this is nothing but the expression which is shown here, equation 1, something like that, yeah. And then if you want, you can perform, if you want to perform a fraction, then it will be like the total number of balls multiplied by fraction of red balls plus total number of balls multiplied by fraction of blue balls. That should be equal to 4 as well. So this is nothing but your equation 2, which is shown here. Yeah, so if don't get scared of this word mass balance. Mass balance is a very easy concept, but what mass balance is easy only if you have the every information that you need. You should know the mass that goes in, and then you should know the fraction of each component in each of those stream that goes into some unit. So if you know that, then it's easy to perform your mass balance calculations. Yeah? So I'm going a bit slow because I want the pharmaceutical chemistry students to know what is a mass balance and is about. Yeah? So it will be unfair if I don't explain this to you. So let's take the equation 2. From equation 2, let's take equation 2. What we can do from this, I'm going to write it again. Fx of plus s1 ys is equal to e1 y1 plus r1 x1, that's equal to m1 xm1. So what we are doing is like I said to you, if you go back to our notes before, or maybe I can write again here. We have a feed line, something like this. If we want to identify something at this mix, some composition at some particular point, we need to calculate. If I ask you to calculate the mass fraction of solute at some point here, then we need this type of expressions. Yeah, so we will do that. We will solve a problem, but we should know, like, don't think like why I care about all these big equations and why I'm deriving it. There is a reason. We have to calculate these values. Yeah, so let's do that. So what we are going to calculate is like xm1. So it's very easy to do. So let's take this part alone. Fxf plus s1 ys, that's equal to m1 xm1. So therefore xm1, that should be equal to fxf plus s1 ys divided by m1. Yeah? This is very simple. Let's call it as equation 3. And we know from equation 1, what is that equation 1? F plus S1 equal to E1 plus R1, that is equal to M1. Or in other words, we can take only this part. M1 is equal to F plus S1. So substitute 4 in equation 3. So we are going, what we are doing at the moment is we gave some notations for everything that goes into the unit and everything that comes out of the unit, and we talk everything in terms of solute. We only care about solute because that's the product that we want to extract, and that's the product that we are interested in. Yeah. So after assigning all these notations, we are throwing all the all these equations to get as many number of expressions that allows you to calculate almost everything that goes inside the system, that comes outside of the system, and if there is some mixture, what will be the composition of solute in that mixture, and what will be the weight of that mixture. Yeah, so we are trying to calculate everything, and we are trying to make use of these two simple mass balance equations, equation 1 and 2, to get all the other parameters that may be difficult to get. Yeah, so we are solving them by mathematically using a set of expressions. So this is when we substitute equation 4 in 3, we will get xm1 is equal to fxf plus s1 ys divided by f plus s1. Yeah, what it says is like so what this equation, let's give this as equation 5. So if you look at this equation, so this is y. If you look at this equation, if we have feed, if we have the composition of solute in the feed, if we know the solvent, the mass of solvent and the composition of the solute in the solvent, then we can calculate the mass fraction of solute in that mixture. Yeah? So that's the equation 5 can do for us. What else we can do? If you want, we can even take the other side of this equation. Say like m1 is equal to E1 plus R1. So let's call this as equation 4.1. So substitute 4.1 in 3. So what we get? xm1 is equal to fxf plus s1 ys divided by E1 plus R1. So let's give this as equation number 5.1. So again the same rule, yeah, like so what we have now at the moment, if we know feed and then mass fraction of solute in the feed, and then if we know the solvent mass and the mass fraction of solute in the solvent, and if we know the mass of extract and if we know the mass of raffinate, then we can calculate the solute fraction in that mixture. Yeah, so I think it's easy, I guess. Then we can derive a bit more expressions out of this. So let's take equation 2 again, fxf plus s1 ys equal to f into what to do, into f equal to f plus s1 into xm1. I think this equation is correct. Yeah. So what is this equation? Maybe I should turn the page. Yeah. My notebook is a very small one, so what I did is like I just expanded this equation 5 here. If you see the equation 5 here, all I did is like I put this equation back here. So maybe I can write it in the next page for you. This video is going to be a bit lengthy. Don't fight with me. xm1 f plus s1, that's equal to fxf plus s1 ys. Yeah, so this is your equation 5. This is nothing but your equation 5. So what we did is like so I want to calculate the f by s1 ratio. So everything will look bit like why are we doing these derivations, but when we are going to solve the problem, we need all these equations. Yeah, it's okay if we have too many number of equations, yeah, because we will have only limited number of data, and then if we need to design an extraction unit, it's better we have all the informations that connect something with something. Yeah, so how to do this one? F1, say xm1 f plus xm1 s1 is equal to fxf plus s1 ys. Take all the f to one side, so xm1 f minus f xf, that should be equal to s1 ys minus xm1 s1 xm1 minus xf. If you want, you can forward the video, you can skip the derivation and take notes of the final expression. Yeah, so but I prefer to derive it, so the students who don't like to see the derivation, obviously they can skip it and just go to see how the final expression looks like. Yeah, so we can calculate f by S1 we take it to denominator, this one goes to denominator of this side, so ys minus x sum 1 divided by x sum 1 minus xf. I hope I did the equation correct. I think fx no, I think I did some mistake. So we already calculated feed by solvent ratio. Something with that relates the composition of your solvent, sorry, your solute in the raffinate side, ys minus your concentration of solute in the mixture and the concentration of solute in your feed. So let's go on to calculate something like E1 by R1. So this is something like extract to raffinate ratio, and then we need to try to connect them with a mixture, something like x sum 1 and x sum 1, and also with the solute concentration x1 y1. So this is your solute concentration in the raffinate side, the solute concentration in the extract side. So we need to try to derive this one and also another one, E1 by M1. So it's easy to calculate. So if we go back to equation, which equation is that? If we go back to equation 2, fx of we have this part E1 y1 plus R1 x1, that's equal to M1 x M1. So this is from equation 2. This is one of your solute balance, mass balance equation, and then we know that M1 is equal to E plus R1. M1 is equal to E plus R1. I think we derived this. Yeah, this is equation 5.1. So let's write equation 5.1 straight away. Equation 5.1 is nothing but x sum 1 multiplied by E1 plus R1 equal to fxf plus S1 ys. So from this you just expand this one, x sum 1 E1 plus x sum 1 R1 equal to fxf plus S1 ys. So all we need to calculate is E1 by E1 by R1. Let's do this. Okay, this solving this equation will give ratio of E1 to R1. So how to expand this equation? So it's already expanded. Put x sum 1 E1 minus you have already R1 here. I think I messed this up completely. I think let me do it again. We know from equation 1 what we know from equation 1. Equation 2, sorry. We know this one like E1 y1 plus R1 x1, that should be equal to m1 xm1. This is your part of your equation 2, and from equation 1 we know m1 is equal to r1 plus e1. So let's plug in this here. So e1 y1 plus r1 x1 is equal to r1 plus e1. So this, the part of derivation is not to scare you, it's also to make you understand how those simple expressions, we had only two expressions, equation 1 and 2, and from the two expressions we managed to get a lot of useful expressions. So that's why the concept of mass in equal to mass out, that might look like a very easy statement, but at the end of the day it will help you to solve a range of engineering problems, not only in liquid extraction, almost any other unit operations that we encounter in chemical engineering or bioprocess engineering, even pharmaceutical engineering. So that's why we are trying to derive these equations. Obviously I can show only the final expression and then just go on to the next topic, but you won't understand, at least you won't understand the benefit of mass balance. So let's expand this equation. I think you should know to do the, at least you should know to do the derivations, and I think it's okay to learn at this stage, like you are studying undergraduate and undergraduate course in pharmaceutical chemistry or chemical engineering. I think this is the good time you will have time to see how the derivation works, how the equations are obtained. Also in the textbook they are not deriving the full expression. They will suddenly show you, like if you have mixture composition, if you know the mass fraction of solute in raffinate or extract or your feed or your solvent side, then you can calculate some ratio using this expression and you will be shocked like where that expression comes from. So it's better to derive it, and then you will know how to do it. So it's also the main purpose of deriving all this expression is, one thing, you will learn something from mass balance, and then you are going to solve anyway the liquid extraction problem, but you should also know the engineering principles. Like we always begin with the two expressions, and then out of nowhere we will end up with like 4 or 5 expressions. So with some that will give you many more useful information than the first two basic expressions. So these are the main reasons that I am deriving the whole equation. So anyway, it's going to consume only extra 30 minutes, so that's okay. So let's take E1 all on one side minus E1 xm1 so let's take this E1 y1 minus xm1 if you are going to write the exam in the like in on campus, then definitely I would have asked you to derive everything in the final exam. But now you will solve some problems. If you expect anything from liquid extraction, it will be some objective type questions and some problems that you might need to solve. Also in crystallization as well. You will expect few problems from both of these topics, because I think these two are really important, especially if you are studying pharmaceutical chemistry. So this is, we derived the extract to raffinate ratio. So this is perfectly fine, I think. Let's give some equation number, say 7, and then what else? I think we have to derive, we have to derive one more, E1 to M1. So extract to mixture ratio. So what's that? So let's take equation 7. In equation 7, we know R1 is equal to, okay, let's put like this one. We know E1 plus R1 equal to M1. This is from your equation 1. So therefore M1 so R1 is equal to, all we need is we need to replace R1 with M1. So we know R1 is equal to M1 minus E1. So let's put 1.1. So substitute 1.1 in equation 7. In equation 7, say, so E1 by M1 minus E1, that will be equal to XM1 minus X1 divided by Y1 minus XM1. So just we need to expand E1 Y1 minus E1 XM1 equal to M1 X suffix M1 plus, sorry, minus M1 X1 and then minus E1 XM minus 1 plus E1 X1. So if you look at this expression, minus into minus plus E1 multiplied by X1 plus into minus M1 X. Everything looks fine to me. So these two values get cancelled, both are same. So what we get at the end is like E1 Y1 equal to M1 XM1 minus M1 X1 plus E1 X1. So therefore E1 Y1 minus E1 X1 is equal to M1 XM1 minus M1 X1. From this we can calculate E1 by M1 ratio. Yeah, it's very simple. This is very tricky. Yeah? This is a very good derivation to be asked in the final exam, but yeah, why not? X1 minus 1 minus X1 Y1 minus X1. So I think we got all the useful expressions out of those two basic expressions from the, which we call it as a mass balance equation. Yeah, so I think we did everything so far. We have to derive whatever that we need to derive. Especially these two equations, say like just to check this equation 7 here, equation 7 and also equation 8. So this equations looks bit weird, but what this equations really states is something like CAB. Say this is your liquid equilibrium curve, and then say this is your feeds point and it comes at your solvent point F S1. If you have a mixture, so according to equation 6, what it says is like so if this is your tie line, if you know this mixing point, if you draw this line and then, no, this is, let me draw it again, a bit clear. Let me draw it again clearly. The diagram was awful. Let's see, like C, A, B. This equation 7 and 8, what it states is like, those are some expressions, some mathematical expression, but what it states is the following. Yeah? We can prove that later when we are going to solve the problem. Imagine this is your F point, this is your 100% solvent point, so just call this is your something like feed line maybe. So if there is some mixture, say point M1, say M1, if we have a tie line that cuts across this particular point M1, it will touch, we know this side is our raffinate arm. You must watch my previous lectures. So this is 100% carrier liquid. The arm which is near to that of carrier liquid, we call it as raffinate arm, and this side will be, if you don't remember which is your raffinate arm, which is your extract arm, just look where is your solvent is. Wherever your solvent is, that side will be your extract arm. So this will be your extract side. So if you have a feed line, if you have some, say some point, that will be your mixture. So any tie line that cuts through that particular point M1, it will touch your liquid-liquid equilibrium on the extract side at E1, and then it will touch your liquid-liquid equilibrium line on the raffinate side at R1. So we will show that, we will realize that when we are going to solve the problem. Yeah. So I think this is enough. In fact, we can even just use this, if you look at this diagram, just to say, like, imagine we have CAB, so if we have something like a feed line, the one thing good with this online lecturing is I can change the color of the line. So let's draw this line here. If I have a tie line, I can even calculate what will be the composition at this mixing point M1 just by using graphical method. Yeah, so you know how to interpret your so if I give you, this is my feed line, or if I give you some problem, my feed contains that many say like my feed, I can design a problem right now. So my feed contains 50% of solute, 0% of solvent. So that say that will be at this point, and then I am using a 100% pure solvent, that will be somewhere around this point. This is your 100% solvent. So now we can draw this line, and then in the exam I can give this type of diagram, and I might even give the tie lines, or maybe, and I will not, I might give some other tie line, say somewhere around here, and then I will ask you to something like say, you may expect something like that in the exam, C A B. You have to draw this feed line. I will not give you, but I will give you some tie lines like this. Say let's put some pink color. One tie line here, say another tie line here, something like that, and then I will ask you to tell me what's the composition at point M. I will assign this value M1. So what's the composition at point M1? So you have to calculate for me. And how to calculate is that, like, if you know the, no, this point is easy. You can tell the composition at point M1. That's very easy because you know how to draw a ternary diagram. So composition at M1 is easy. And then I will ask you to give the composition of that tie line that cuts through this point in the extract side and the raffinate side. So you have to draw the correct tie line. I will teach you separately how to get additional tie lines in the image. So something like this, and then you have to tell me the composition of extract here, and then you have to tell me the composition of the raffinate here. So you have to draw this green line by yourself. Yeah, you have to draw the correct tie line. This is a bit tricky to, but anyway I will show you how to. If you have something like CAB, sorry for going a bit slow, but this is very tough topic, believe me. Like probably if you read a book like there are few very good books on liquid extraction, but the problem is they won't give the full details, you know, like you can understand the book, but you have to spend a few months to understand what they are talking about. So that's why pay attention, and it's okay to go slow this topic. So if you have some good liquid equilibrium curve, and if I have tie lines like this, if you don't remember what is a tie line, you have to watch my previous lecture for sure. So this is tie line 1, this is tie line 2. If I ask you to draw a tie line that cuts through this point, you cannot just use a scale and draw like that. Yeah, this is wrong. So there are few correct methods to generate additional tie line. I cannot draw in the paper and pen using. I have to load the graph on the PowerPoint, and then I will try to show you like a separate video. We have to generate additional tie lines. I think this is enough for this lecture, because I think if I give you too much, you won't read it at the end. So try to watch this video, try to take a notes, try to derive it one time, and then in the next video I will show you some rules that we need to, or if you want we can call it as a graphical method, or we can just call it as like rules, like a thumb rule, or maybe we can even call it as a chemical engineering rules. So that way we will learn how to exploit the ternary diagram in order to get some design quality information from the ternary diagram. Yeah, so I will stop recording now. Thanks for listening.